So, welcome back. Good afternoon, you all. So, in the previous class, I think we have discussed about uh, how we can evaluate the ground state of a harmonic oscillator using a ladder operator or so-called creation and annihilation operator, A and A dagger. And from that, I think you remember that we derived also the uncertainty principle for the ground state, which is exactly equal to h bar over 2. And this is the minimum. So if you derive same way for the higher excited states, then obviously this uncertainty will be higher than the h bar by 2. That you can try and prove. Okay, now since we have all just shown how to get how to obtain, how to derive the ground state psi naught, perhaps we should try finding how to get excited states of a quantum harmonic oscillator from the ground state. If ground state is known, then how to get normalized excited states. And also it can be possible also if you know any arbitrary eigenstate, any order, need not be ground state. So by use of your so-called creation or annihilation operator, you can find the immediate higher excited state or lower excited state. So we tried doing that now. For the concept, you know here that first line, if you see that if psi naught is the normalized ground state, then if you just operate your so-called lowering operator or annihilation operator, since there is no state available below ground state, so we force that result should be 0. Similarly, if a ground state, if you are just using a creation operator, then it will be called, you will get the just immediate higher state, first excited state. Okay, so this is the concept, and we have actually shown that earlier, and also here we will be trying to find how to get the normalized things. So also I think we have shown that the ground state psi naught has eigenvalue E naught of half h card omega. Okay, that's the 0 point energy corresponding to the ground state. Ground state distribution is Gaussian if it is one dimensional potential. You are considering that thing. Okay, so now this equation, this concept, this psi naught is having a eigenvalue of h card omega by 2. Then we know that the Hamiltonian, this is the Hamiltonian, you know, a dagger a h bar omega plus half psi naught. This is the Hamiltonian. If you are writing a dagger, then it should be minus half. So one of them you can use. Here we are using just the a dagger a plus half, and you should keep in mind that this a and a dagger, they commute by 1. So that means a dagger minus a dagger a should be equal to 1. That is what we have derived earlier. So those things again and again we will be using. So in this case, if you just operate Hamiltonian on ground state, psi naught, so obviously you're supposed to get the eigenvalue of h bar omega by 2 and psi naught. That's a eigenstate again, ground state. So all the states will be eigenstates. That is how we get. So this is your equation number 171, and you proceed from here how you can get a generic equation. So what you would do, you just left multiply a dagger both sides, or you can say that you operate again a dagger left hand side and right hand side. If they are identical, so left side whatever operator you are operating, right side if you operate same operator, then you should get same thing. So that should not be any problem. So because they are identical, so you are just putting it, because h bar omega is a constant, so we are just putting inside. So here was a dagger a was there, you just add one more a dagger, and 1 by 2 we are just writing a dagger by 2 and psi naught. And here again h bar omega by 2 constant, we are just operating a dagger on psi naught. Now we try to do little trick here. What you do, whatever insight is there, you just take a dagger is common now in both cases. That means whatever you, sorry, a dagger, sorry, I should not take common here because that is multiplied. So what you do, if you just leave the first operator a dagger, that means you are getting a dagger a, right? A dagger a you are writing from the commutation rule. You know, a dagger minus a dagger a equal to 1. So a dagger a can be written as a dagger minus 1, and this a dagger left as it is. So we are just expanding it using the commutation rule. Okay, as it is I am leaving everywhere. So now you do one thing, this a dagger, right, a dagger, and if you just multiply this thing, a dagger multiply to minus 1, that means minus a dagger and h card omega and psi naught, that I take right hand side. Okay, then left hand side, what will be left over? A dagger, this one taken to the right side, and then a dagger by 2. So a dagger has been taken common again. Okay, so right hand side here will be a dagger, that a dagger taken outside. Okay, little bit you think about that, this is coming like this. So a dagger minus this term goes outside, and then you are having a dagger a dagger, and then a dagger by 2. A dagger you take right side is there, so you can easily take right side. First you have to operate a dagger, so I can take within that. So a dagger I operate first, then I will be operating the entire thing. That is what the idea. And right hand side, when one a dagger comes here multiplied by h bar omega, then you get, already you have a half and another one came, so you get again a dagger this thing. So from 174, equation 174, just observe this. If you are just considering this is another eigenstate, this is another eigenstate, and you are operating what? This is again Hamiltonian. So if you are Hamiltonian again, if you operate, that means you are getting these as a value, constant, real value, and then again same function. That means this is your eigenvalue, right? So this one again we know that from the first line here I have written a dagger psi naught equal to psi 1. So I write psi 1. So psi 1 equal to this one. So what I observe, that if you are operating on psi naught, then you get psi 1, and then 1 unit of h bar omega is added here. So similarly we can write from this again, I can write psi 2. When I am replacing 1 to 2, then 1 will become here 2, then psi 2. So same process you repeat, and then you can get again psi 3, so 3. So whenever you are putting 3 here, you are getting 3 here. So ultimately if you are putting psi n, 1, 2, 3, 4 up to n, then you have to write n. So that is how you get your En equal to n plus half h bar omega. So that is how, using your a dagger a Hamiltonian, you express your Hamiltonian in terms of a dagger a, then your eigenvalue is coming like En equal to n plus half h bar. Okay, and so in this case, if you just think about that, this one you are operating on psi n, a dagger a, half is half remained, and a dagger a, if you are just operating on psi n, you are getting a number n, integer number. That's why a dagger a is called a number operator. So if you write like that, a dagger a is just a number operator. Instead of that, if you just write number operator, sometimes whenever it is written just a number operator, you can replace by this A dagger A terms. A dagger A is known to you. So good. Up to 180, it is clear that from the if you express your Hamiltonian operator in terms of your raising operator and lowering operator, then you get the actual eigen energy or nth1. Now, so this number is A dagger AN. Suppose you are just operating on psi n, you are getting n psi n. So you can write in bracket notation like simply like that. Okay. Sometimes this psi also not written in some textbook. They continue. They actually consistently they omit psi. Just the subscript, that is the eigenstate number they express. So because you are, whenever you are using bracket notation, you don't need what is the function, what is the, it is a x dependent function, what it is all about, you don't need to know at all. So only thing is that which eigenstate you are dealing with, the number, the n is important. That's why it is occasionally written, instead of this one, you write just operate on nth eigenstate with a number operator, then you get n multiplied by same function. That means this is your so-called, you can say that like a eigenstate. Okay. So now again, if you see, suppose you have a psi n nth eigenstate, it is known to you and you know that that is normalized. Normalized means you know that if you take inner product with itself, then it should come 1. Right? That is actually normalized. Suppose this is given. Now, if you operate with a creation operator here, then you're supposed to get psi n plus 1. But after operating, you are sure that you are getting psi n plus 1. By the way, it is not a eigen equation. Because A dagger psi n, it is not giving a number against psi n. It is giving another function, psi n plus 1. Right? A new function, higher order state you are getting. But you don't know this psi n plus 1 is normalized or not. That means you don't know this psi n plus 1, if you are taking a inner product with itself, it will be coming 1 or not. You don't know. May not satisfy normalization condition. Okay. So to satisfy that one, this A dagger psi n, inner product if you take, that should be 1. So we proceed with following things. Suppose whenever you are doing like this, that you are getting a new function, right? When you operate with psi n, you are getting a new function, and then you add, you just multiply a constant, namely an plus 1, because multiplying this, whatever you will be getting, you're supposed to get a normalized psi n plus 1. So after operating A dagger, you're supposed to get psi n plus 1, but that may not be normalized. So we multiply a normalization constant, then whatever we get, that is for sure normalized. So that way we understand. So when you operate, that may not be normalized as I mentioned here, but if you just multiply a normalization constant, you can get a normalization. You have to find out what is the normalization constant should be. So to find out the normalization constant, what we try to get? We try to get an inner product with itself. So you take inner product with itself means you have to add multiply. You have to have a bra function, and then an plus complex conjugate, that will come an plus 1 whole square. So if you take inner product with this one, that means this term will come square, and then bra A dagger n and kate A dagger n. That means you are taking an inner product, and that you, if it is a normalization constant, so this inner product as a whole should become as 1. Right? Now you see, you do a little bit work on it. Just an plus 1 whole square, you keep it. And what you do, this A dagger, you take to the this side. Because you know this A and A dagger, they are Hermitian to each other. They are Hermitian conjugate. So whenever, instead of operating with a bra function, if you are operating in the kate one, then you have to use the Hermitian conjugate. So that means A dagger, if you are taking to operate on the Kate function, that will become A. That has been proven earlier. From the function itself, you can see also that whenever we have defined A and A dagger, that's complex conjugate there basically. Okay, so we write this one. So that should be equal to 1. So this equation I can just write in this form. Left hand side I can write in this form. Okay, now you see, if you operate A dagger on n, so what you get n plus 1, right? And then again you operate A lowering operator, then again you get n, right? So that means I am writing like this. I think this one should be hide. Yeah. So whatever I am writing, A dagger A n plus 1. It should be n plus 1. I think this n is there here, and we are writing, I think this is some typo error, it will be there. So I think this will be ultimately this one you will be getting, n plus 1 you will be getting, right? Because whenever you are just operating n plus 1, then you get n plus 1, and then again you are operating on n, then you get n. So that ultimately you are getting 1. Okay. So what that means, this, if you are taking n inner product with n, then it is 1. So that means a n plus 1 square equal to 1 by n plus 1. So in the next slide, what we can write then, a n plus 1 is defined by 1 over square root of n plus 1. So if you write a n plus 1 as this one, then that will be normalized. Okay. So in this way we can write that n plus 1, if it is a normalized one, that means psi n plus 1. Whenever I am writing n plus 1, that means it is a psi n plus 1. That psi n plus will be normalized once you operate n with a dagger, that has to be divided by this one. So that is n. Instead of a n plus 1, we are writing like this, 1 over this one. Okay. So you can go to the, you can create your higher excited state from n to n plus 1, but to have it normalized, you have to normalize with the square root of n plus 1, right? So from this equation, what you can write, if I write a dagger n, then I can write a dagger n, and this n plus 1 square root of n plus 1, I can take this side, so we can write n plus 1, this one. So this is the standard equation. Okay. So if you are operating a dagger on n, Kate n, then whatever you are getting, you have to just multiply square root of n plus 1. Then this n plus 1, that means psi n plus 1, that is actually normalized one. That can be considered as a normalized one. Okay. So similar fashion, in a similar fashion, if you start with a operating on sign, I think this a symbol should be like this. I think this should be modified. Typo error here. So this a, if you are operating on psi n, that means it is a lowering operator, right? So it's supposed to give psi n minus 1. So if you are just multiplying normalization constant, then it should be normalized. Okay. So you just process again same fashion, an you will be getting, and if you take that side, then you are getting lowering, and then again raising, then again it will be coming at the same one, right? So in turn you are getting n. Whenever you are just operating on a dagger n, so you are just, you can say that you are operating a dagger a on n. That means you are getting n. Additional n you will be getting. This is a number operator. No, this a dagger a is a number operator. So number operator, you are operating on n. So that means you will be getting n. So n will be outside. So when n is outside, that means a n minus 1 will be 1 over square root of n. So that means I can write, whenever I am operating lowering operator on psi n, then I supposed to get psi n minus 1 normalized one whenever you are multiplying square root of n. So this relationship holds. So these two equation is very important, 185 and 188. 185 says you are operating, n is the normalized one, psi n, you raise it, then you get another normalized one multiplied by this one you will be getting. Okay, but if you are using lowering operator, then square root of n, they are n plus 1 because it is raised to n plus 1, and it is though it is lower one, but here it will be square root of n according to this one. Okay, so this thing should be clear now. If you have any question, you can ask me. Okay, so now if one starts with a normalized ground state, suppose 0, normalized ground state ket 0. Ket 0 means psi 0. Psi 0, inner product psi 0, you get 1, right? That is normalized, you know, because you have already solved earlier psi naught, and that is normalized, you got already. Then what you get, the generic function for the state n can be written as, from the 0, if you try to first you just raise a dagger, then you get n plus 1. Next a dagger, you get n plus 2. Next a dagger again, n plus 3. So in this way, to get nth eigenstate, excited state, that means you have to operate a dagger to the power n on naught, and in between you will be keep on getting all the constant terms, n plus 1, n plus 1, all those type of things are there. So in the denominator, it will be you will be getting n factorial half. So generically, you can just start from the ket 0 and operate a dagger, whatever you are getting. Then you operate again on that one, again a dagger, and keep on getting, and then you will be getting like this. Summarize, you can get in a compact form like this. And a reverse way, you can prove also this thing. So here we try to prove in a reverse way. Suppose you have a nth function here, a dagger, you know this thing. A dagger n is this one, that is what we have learned earlier. Okay, from it you just that particular equation 189, equation 189 in the previous slide, whatever we expressed, the same thing I am writing. And what I do, I just multiply square root of n plus 1 in the numerator and square root of n plus 1 in the denominator, right? And ket 0. That means that 189 equation I am writing only this factor I multiplied here, numerator and denominator this factor, right? So what we do here, this one if you multiply here, so n factorial means you know n times n minus 1 times n minus 2 times n minus 3 and so on, and then square root of it. Now n plus 1 you also include there, multiplication is there. Then it will become n plus 1 factorial, square root is there. So bottom you are getting square root of this one, right? Now you operate a dagger, both side. One more creation operator you try, left side and right side. If you do that, then this a dagger to the power n will become a dagger to the power n plus 1 to this one, right? Now you see, if you just little bit carefully look into it, then it will become n plus 1. If you are just n plus 1 times, if you try to operate on this one, 0, right? Then you will be getting n plus 1. Ground state to n plus 1, if you get n plus 1. And then you will have n plus 1 will be there, because additional factor will be, multiplication factor will be coming, and that will cancel the denominator term, because the factorial will be there. You just keep on operating n plus 1 time, that means you will be getting additional n plus 1 factorial in the numerator, and that will be cancelled. So this n plus 1 will be left over, so you can write. So you can, both way you can just prove that a dagger n plus this one. But why I am showing this, because this is the generic function you can use, that if your ground state is normalized 1, then you, if you want to get any, suppose 0 you want to get 5, then you just put here 5 and here you put 5, and then you get the normalized eigenstate for the 5th excited eigenstate. So this thing you can just keep in mind. You can solve or you can keep in mind. All right. Now, as I told you that this is raising operator, lowering operator, everything is fine, and they are actually representing any operator. They actually represent your what you call that, equipment, measurement instrument, right? So if you can actually design a hardware, if you can design a hardware that can give this type of represent this type of operator on any quantum particle, that would be fantastic. And normally any hardware, any instrument, any device you plan, design, and that you get that you will have an input and you will have an output. So input to output, you can just get if you know the transfer function of the device. So that transfer function of that device you can represent by a matrix. And if you know that matrix, then you can actually numerically, you can quickly calculate. So here we'll be trying to understand that for a quantum harmonic oscillator, we know that how it can be, Hamiltonian can be represented by lowering operator and raising operator. Now we'll try to find out if we can represent Hamiltonian of a quantum harmonic oscillator in terms of matrix. So to do so, what we do is just start first with the raising operator. Okay, raising operator, that means sometimes they are, as I mentioned, raising operator or creation operator, and other one is the annihilation operator, and together combined they are actually known as ladder operator. Okay, so if I try to find out the matrix element of the raising operator, AMN means if you have a mth row, nth column, then you can get a dagger mn, and then lowering operator also you can get AMN. Now you try to find out the matrix representation of the operator. Earlier we discussed any operator, if you try to find out the matrix element, then matrix element for a given basis vector set. So here basis vectors are your all eigenstates of the quantum harmonic oscillator. Psi naught, psi 1, psi 3, psi 4, they are actually basis vectors you are considering. Okay, so those basis vector, they are subscript indices, we can represent with a number as I mentioned earlier. So the matrix element can be represented as just expectation of this one. Overlap, you just operate with one basis vector, then whatever you get, you take inner product with another basis vector, then you can get whatever the value, that is the matrix element corresponding between these two eigenstates, basis vectors. Clear? So if we accept this one, that is what we have learned earlier, that a operator, if you represent in a matrix form, that in a bracket notation you represent like this. Now you look carefully, a dagger n. So you are operating on n. So you know what you are supposed to get. You will be getting n plus 1 and multiplied by n plus 1. That is what we have already shown here. This 191 equation, this one I am just writing exactly that one. N plus 1 being a number I have taken outside. Right? So now AMN dagger, this is the expression. Right? And this is the inner product between m and n plus 1. And you know they are eigenstate and they are orthogonal, because all the eigenstates, functions you find, they are basically orthogonal. So they will be non-zero, 1. It's a kind of delta Kronecker function. If am equal to n plus 1, then only they will be 1, otherwise they will be 0. If they are orthogonal, that means only the psi naught, with psi naught you will get 1. Psi naught and psi 1, if you are just giving inner product, then you are supposed to get 0. So this will be actually valid only when m equal to n plus 1. Otherwise all things are 0. So now again you know that this m or n, that is being it is coming from quantum harmonic oscillator, they start from 0. Right? So m equal to 0, if you just put m equal to 0 and n equal to 0, that is the first element you are supposed to get, right? M equal to 0, n equal to 0. That means this is 0 and this is 1, right hand side. 0 and 1, you take inner product, that means you should get 1. 0 means psi 0 and 1 when it is there, that means psi 1. Psi 0 and psi 1 inner product, they are orthogonal, that will be 0. Now m equal to 1, n equal to m equal to 0, n equal to 1. Right? So you keep m equal to 0 and n you run over, then you get the first row. Right? M equal to 1, then n again vary from 0 to infinity, you get second row. And m equal to 2 and then n vary from 0 to so on, then you get third row. So if you put down all these things, then you get this matrix. So the diagonal and upper diagonal, everything is 0, and just neighboring the diagonal terms, you are getting that, you see, square root 1, 2, natural number square root you are getting. So this is actually a standard way to represent a creation operator or so-called ranging operator in a matrix form. So if you want to get a dagger psi n, that means you have to multiply that corresponding psi n function. Then whatever the value you will be getting, you're supposed to get. That I'll come later. Clear? So now you see this one. If you just try to find out what is the matrix element for the lowering operator also, AMN, same way, same fashion, you can just put AMN equal to this one, and then since it is a lowering operator, if you operate on that, then you are getting square root n, right? Square root n will be there, and n minus 1. Square root n being a number, you are taking outside, and then same way, delta Kronecker function, m equal to n minus 1 will be 1, otherwise it will be 0. Then if you just try to construct the matrix, being m equal to 0, n vary from 0 to so on, and then you are getting this function, this matrix. So now you know the matrix representation for A dagger and A. So you can find Hamiltonian now. Hamiltonian is what? You know that H bar omega, A dagger A plus half. Since this is a matrix, so this half, you cannot write just simple half. You can just write a actually one unitary matrix. Diagonal values will be there. Okay. So if you just multiply A dagger and A, and then half only in the diagonal part will be there in a matrix in the same order. If you just try, then you get this equation. Just note down that this is the Hamiltonian. This is the H bar omega is there, H bar omega is there, and A dagger A. So you have now a matrix, very nice matrix for a quantum harmonic oscillator. Okay, you don't need to bother about your A dagger A and whatever the things are there, H got omega, and this is your matrix, Hamiltonian. If you have any state, eigenstate, in terms of some kind of vector, then you can just operate vector. Vector means with a basis vectors, basically. Then you can just operate and you can get the result. So that is very easy. Okay, Hamiltonian we could express Hamiltonian matrix, right? Now I want to see if I have Hamiltonian, now I have to represent also eigenstates also in matrix form. If my operator is in a matrix form, all the eigenstates can be a basis vectors, right? So those basis vector, how we can represent? Suppose you have a ground state 0, psi 0. Psi 0, then you have, suppose from starting from 0, psi 1, psi 2, psi 3, psi 4, up to psi n, nth eigenstates are there. So nth basis vector. So you can have a Hilbert space, n-dimensional Hilbert space, all the vector space. Then when I want to represent psi 0 in a vector form, what I will put? I will have a column matrix, because nth dimension, nth element will be there in the column matrix, but since it is a 0, only the first element will be non-zero. And non-zero, what any just non-zero value, we just put simply 1. It can be any number. Okay, we can show that it can be any number, that does not matter, but it is only first element is available, non-zero, all others are 0. So that eigenvector of the ground state, that is one basis vector, and that we represent this one. And then first excited state, what we do? Another basis vector, right? So that will be in another direction. So I can have another vector with only second element will be non-zero. we are putting 1 here. Similarly 2, third element, 3, fourth element, and so on. In this way, if I want to get n, that means 0, 0, 0, 0, 0, nth element will be 1. That is how your eigenstate you can represent. You don't need to bother about whether it is a function of x and y and so on. You want to just deal with the mathematics. You have a hardware, you know the eigenstates, and then you can just operate. You just represent ground state like this. And then if you see, if you are operating Hamiltonian on these, what you supposed to get? This is a ground state, right? If you just operate this one on Hamiltonians, you have a Hamiltonian function here, Hamiltonian, and then you have a vector of nth dimension vector, that basis vector 1, 0, 0, 0, 0, and so on. So if you multiply, then you get half h card omega, and same vector will come back. So you can do that a0 if you operate, you will get this function. Similarly, if you are just Hamiltonian, you operate on this one, you get this one. Hamiltonian you operate on 2, then you get 5 h cut by 2. So Hamiltonian, if you operate on nth eigenstate, with you supposed to get nth eigen energy, just you look 198. Whenever you are putting 2, that means you are putting 5 by 2, right? 2 plus half. Whenever you are writing 1, that means 1 plus half. Whenever I am writing n, that will be n plus half. Okay, so that is clear. If you are just representing your basis vectors like this and Hamiltonian operator in this type of matrix form, you see diagonal matrix, it is actually only diagonal matrix, and diagonal values are actually eigenvalues for that matrix, right? So you get this nice equation. And here just I mentioned that you can also prove that a dagger E equal to n, just simply with this format you can just try. They are also shown, it is in this way also you can show that a dagger this one. And you can also try to show this number operator, that means a dagger A is the number operator, and if you try to commute with a, then you will be getting minus a. So sometimes we will be using this function, that's why you can prove yourself. A simple method you can try, I leave it to you for derivation. And similarly, number operator with a dagger, you get a dagger. So this thing sometimes we will be using, just as a home task you can try. Okay. Now, it's a very nice thing that we have demonstrated a dagger A in terms of matrix. Now we know that this position operator, you remember position operator we can actually express in terms of a dagger A. A dagger A can be represented in terms of position vector and momentum operator. Similarly, we can just in reverse, we can just get back your momentum operator and position operator in terms of this ladder operators, all this a dagger. Now you know a dagger, you can try to find out what is the position operator. So position operator also you can write down in a matrix form like this. So in terms of you know the expression of x in terms of a and a dagger. A and a dagger you know you have represented with a matrix. Use that matrix and then just simplify, you will be getting this one. Similarly, momentum operator also you can get in a matrix form. So everything now from very complicated mathematical expressions, second order differential equation, etc. Now you have everything linearized. Now you have all the matrix and all the just basis vector you can use, and you can operate, you can get this ultimate things. Okay. So this is useful for actually handling quantum particle, quantum computations, quantum operations, all those type of things. This will be useful because once you can represent your Hamiltonian for a system, then everything done. Okay. Now another one thing, suppose you have a eigenstates, you know, in a quantum particle m, mass m, if it is in a potential parabolic potential, then you know that this quantum particle can stay in psi naught ground state or one of the excited states. But there is a chance that you can design a hardware or surrounding system is such that the quantum particle can stay also in a superposition state. Even if it is not in a superposition state, you can modify, you can pass it to a certain hardware, it can become superposition states up to eigenstates. Okay, how that can be done? Now you just try to find that thing. Suppose you want to get a superposition state like this, psi naught and psi 1 with a weightage of k naught and k1. It can be consider that k naught square plus k1 square equal to 1. That's a quantum particle total probability is 1. Probability of this one is k naught square and probability of psi 1 is k1 square, so total probability will be 1. That can be maintained. Now you want to generate this one. Now little bit you look into it, you are writing k1 psi naught. Now second term k2, instead of psi 1 you can put a dagger psi naught, right? Now what you do, if you are just taking k2 k1 by k2, you just k1 you are taking as a factor, right? If you are just taking a factor k naught and then k plus a dagger, so k naught k equal to k1 and just k naught equal to k2. This way I just represent. Okay, k naught and k are constant, then psi naught. So what you have a ground state, then you have a creation operator. Along with that, this constant term does not matter. That's only the normalization factor you can just consider. So that means a creation operator, and if you add one number with it, additional number, creation operator you add on that. If it is a matrix, then it is k multiplied by some unitary matrix. Just unit matrix. So diagonal value will be one only. Then you add them, then you operate, then you get a superposition state. So if you can design a hardware which reflects this operator, a dagger plus some kind of number, then you can create a superposition state. So this is very important, because frequently for any quantum operations we need to get superposition states. Okay, in quantum computation, you know, this Hamadat gates, all those type of things, normally we get superposition state we can create. So this is actually the ultimate way. Fine. So now you see this ladder, I again just written down the ladder operator. So this ladder operator means you already know that I have mentioned that a dagger, sometimes in short they are called together as a ladder operator, ranging operator. And again, these ladder operators can be time dependent. As you know, we have already discussed earlier that we can consider that operator is time independent. Wave function can evolve over time. That is actually Schrodinger picture. And sometimes it is helpful to consider operator as a time dependent. Your wave function is static. It is not changing over time. So that type of operator, if we just represent some representative operator A as a function of time, and we have shown earlier equation 131, if you see, I think a couple of lectures before we discussed that the operator is this, that can be, that operator commute with Hamiltonian and multiplied by I over h bar. That is actually time derivative of AT. So this expression we know. Now this AT, it's an arbitrary operator, okay, operating in the system. You are putting as a just lowering operator A. We are just considering A. This one, as you are considering that your ladder operator, one of the ladder operator is time dependent. Then I can write this one. This A will be replaced by this one, right? And this Hamiltonian we can write like this. Hamiltonian here, h bar omega a dagger A plus half. And this operator, if you just remember correctly, this time dependent operator can be expressed like this. You know, this is your e to the bar IHT by h bar. You just recollect a couple of times back that psi naught, psi, this one you are taking expectation value. When time dependent evolution, you are just clubbing with your actual operator, then that will be together, it is called as a time dependent operator. So time dependent operator AT instead of AT, we are writing like this, right? That is your time derivative. Now, if we just little bit work on it, so you have I omega, this one, a dagger, a dagger. Can you just identify how we are getting I omega here. So EH cut, EH cut I am just putting here. That means I is there and one more H cut omega is there. This H cut omega, that multiply, that is I omega you are getting, right? And then we are writing like a commutation form. We are just putting AB minus BA. In this form we are just writing. And in that case, this constant term will be cancelled. Half term will be cancelled. Half H cut omega, that will be cancelled. If you just, this is one first operator and this is second operator. That means if this is X, this is Y, XY minus YX. And if you do that, this constant term will be cancelled. Only this thing and this thing will be there. So first term will be A dagger AA minus AA dagger A. And both sides this will be there. Right? Now we little bit carry forward this A, this right side operator A, I take outside, right? Then what you get inside? A dagger A minus AA dagger. You know, A dagger minus A dagger A, they commute with 1. So it is a reverse thing is there, so minus sign is there. A dagger minus A dagger A, we have earlier proved that they equal to 1. Since it is minus is there, so minus. Let me get this one. So you get this one. So this is actually in fact your AT. So that means DAT by that means time derivative of the lowering operator, you can write like this. So in that case, if you solve this, this is a differential equation, right? So AT you can solve. So AT is nothing but it is e to the power minus I omega t A. So time dependent operator, even though I know that that can be written like that, without Hamiltonian, we can just simply simplify it as this one. So that is actually lowering operator. Time dependent lowering operator is this one. Whatever expression you have, time independent one, you multiply with that, then you can evolve. You can consider your wave function is not changing. Similarly, you can write down for A dagger is this one. So using this time dependent part, I can also find time dependent position operator, time dependent momentum operator. Okay, this way I can express. Any question till this point? If not, I proceed here. So now next thing. This is very crucial now. This from here onward, we are trying to make a transition. So far we have discussed harmonic oscillator, and harmonic oscillator we have solved with quantum way using quantum mechanics. So quantum harmonic oscillator, and we solved all the eigenstates and their solutions, eigenvalue En equal to n plus half h cut omega, so and so. And we promised that electromagnetic wave is actually can be represented, mode of electromagnetic wave can be represented like a harmonic oscillator. So here I just try to show you how that is possible. It is just straightforward, very easy to understand. So far whatever you have learned, just concentrate this one, that would be very, very useful. Now onwards we'll be considering, we'll be moving towards now electromagnetics. Now light wave, we are just moving. We no more mass we want to consider. Okay, like a simple classical quantum mechanics, we don't need to bother much. Okay, so we write this one as a quantization of electromagnetic field. Just we are starting quantization of electromagnetic fields. Electromagnetic quantum harmonic oscillator. From your Maxwell's equation, you know, if you have a electric field and magnetic field, electromagnetic wave, energy density at any point, using Maxwell's equation, we could find this one, right? E cross D, E dot D is the displacement vector, and H dot B, right? This thing is known from Maxwell's equation. We can show earlier also, we have shown somewhere in our previous slides, right? Now you just little bit modify it. Epsilon 0 by 2 ERT, that means epsilon D equal to epsilon 0 epsilon E. So we are considering that this D and E in the same direction. Free space we are considering, of course, free space. So they must be same direction. So I also put R and T, position, at a particular position, what is the electric field, and particular instant of time also I'm putting. That means the energy density at any position, that is time dependent. At any R position, that must be time dependent, because electromagnetic wave will be propagating, right? Similarly, right hand side I convert into H into B. That means I know H equal to B by mu naught, free space. So B by mu naught. So whatever coming, 1 over 2 mu naught, this one coming. Okay. So equation 213, I'm just writing energy density at any point position R at any instant of time. You are just getting like this. Now, to express U as a function of single variable, here two variables are there, E and B. We try to find out, because E and B always they are related, you know, through Maxwell's equation, Carl equation. But it would be easier if we use a vector potential, ART. This is, I think, in your, I think if you have taken some advanced electrodynamics course, electromagnetic theory course, I think that is frequently used normally. But you don't need to bother about much. It is just you consider that it is a new variable you are introducing, and that is actually related with electric field through a so-called Coulomb gauge. That is defined like this. E, electric field, is defined by this. This is called Coulomb gauge equation. So that means this. What is this phi? Phi is the potential. So gradient of the potential. Potential means, you know, that normal voltage V1, phi 1, whatever the potential definition is there, that is the potential. Gradient of that potential plus time derivative of A is negative sign, is E. If you are considering this part is 0, then you know E equal to minus grad phi. That is known. So this is gauge equation, because you are adding one more function, you are introducing forcefully another one vector potential, so-called vector potential, you are using this thing. And along with that, it has to satisfy one more equation, that magnetic field is also can be expressed in terms of A. Curl of A equal to magnetic field. So these two additional equations we have to deal now. But it is a free space, so you can consider that there is no charge distribution, etc. is there. So you can consider delta phi equal to 0. That means equipotential, every potential is equal. So delta phi, gradient of phi equal to 0. So what does it mean? E equal to, then, if it is a free space, E is reduced to minus del A by del T. Right? So that is delta phi equal to 0 we are putting. Again, further, you know that divergence D equal to 0. And if it is free space, divergence E equal to 0 also. Right? And divergence E means E. This one, this equal to minus del A del T. Since it is divergence, that is only space dependent function, del X, del Y, del Z. So del T can be taken outside. Then if divergence E equal to 0, we can say that divergence A equal to 0. Right? So when divergence A equal to 0, we will actually use this one later. Before that, so this is the auxiliary equation we just derived, it will be useful. Okay. Now to make connection between electromagnetic energy given in equation 213 with the total energy of the simple harmonic oscillator, that is our ultimate goal. We want to show that electromagnetic energy is actually equivalent to energy density is equivalent to energy of a quantum harmonic oscillator. We express this ART in terms of this one. A, you know, A is a function of E. It depends on E, and also B, they are related. So we can express something like that, ART, in terms of just Fourier components. Fourier components means, because E and B, you know, they are plane waves. Right? Actually, what I can do, the time dependent part, I can just assemble with the A and the different plane waves k e to the power I k dot r. All the k you are integrating, then you get an envelope of ART. Okay, so that means in terms of k and r, you can just interchange Fourier transform. This is 2 pi power 3 by 2 means it is actually 3-dimensional. That's why it is, otherwise square root 2 pi. 3-dimensional. That's why, that means kx, ky, kz, all this will come. Then that is the function, constant term will come. Okay. I'm afraid that after 1 hour maybe recording will be stopped. So I think I can stop here. I think because that need few one more slide I thought of completing, but I think it will take a little time. I can stop here, and maybe I will continue in the next class. And tomorrow I think also will be class. I think assignment will be discussed tomorrow. Yeah, this I stop now.